Hey guys, we're trying to get our stickers over there on the wall, right? So we're gonna practice being a one and done. Let's do it. In our worksheet here, in our packet on 218, they give us an opportunity to practice. Now notice on page 217, it gives us our steps. So if you need some help walking through your steps, I think many of us probably know it already, but this walks it through with us, okay? So I'm just gonna use this as a guide. I've taped this down so you can't see 218, so it doesn't move. So I'm gonna go ahead and do a goodness of fit test. Let's do it, okay? So it says state, I have to do my H sub O and H sub A, right? Now they said for a goodness of fit, it's just the specified is correct, they're not lying, and the whatever the distribution was is now not correct. So I just have to add in my context, okay? So my question says, these observed counts were determined, use the observed counts to determine whether or not you have convincing evidence that the die is not fair. So you want to be able to say that the die is not fair. That must be your alternate hypothesis. So the distribution of die outcome is not fair, okay? The distribution of dice outcome is fair. So what would be fair? Well, fair would be if I got the same each time. Okay, so let's think about this for a minute. We'd assume that we randomly rolled the dice each time, so we should say the die was random. Which just means we rolled it each time the same way, you know, we didn't throw it any higher or lower, whatever, you know, we were consistent, so we should get different outcomes. And we need our expected counts to be at least 5. We want them greater than 5, but they can be greater than or equal to 5, right? And then and this is actually in our notes. So it's saying the data must come from a random sample of the population. When sampling without replacement, check that the population is at least as large as 10 times the sample. So we have independence because it's safe to assume that we could roll the dice 300 times. Our population of dice rolls is greater than 3,000. Now, this doesn't really make sense, right? But I can write it and you won't get counted off for writing it. All right, so my expected count, I need I've got my observations, right? This is your observed table. And you need these expected values. Now, today we had 2 tables. But back when we did goodness of fit, we just added a line here. Now I kind of wrote over this, but we could put it right underneath there. So this is the frequency we found. We found 42. What would we expect? Well, if you rolled it 300 times in total, wouldn't you expect equally each time? So to get expected, we just take 300 times 1/6 because there's 6 possible outcomes. Okay. So if it was a fair die, we actually know we should get slightly different each time, but we should expect 50 each time. And these are our expecteds, and this is our observations. And I'm just kind of rewriting that so you can kind of see them side by side. So like this is off by quite a bit, right? This one's only off by 5, right? This one's off by 8. That one's off by more than 10. This one's off by more than 10. So 2 of these are off by quite a bit. You can just see by looking. So, but are they off enough to say that the dice, to be able to say that the distribution is not fair? Okay. First off, we're still in our plan, and so did each of our expected counts greater than 5? Yes. 50 is greater than 5, so we're good there. Make sense? All right. We got to do this in our calculator, or we can do it by hand. So we have our formula, observed minus expected, squared over expected. And remember, we have to add them all up. So that's a summation symbol. So observed, again, the top one is observed. So observed minus expected over expected. 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 Observed minus expected squared over expected. Observed minus expected over expected. All of this is going to add up to a chi-squared value, and this back in my table is going to give me a p-value. Once I get my p-value, I can conclude, right? Feeling good about this? Now this one's only 6 numbers. We could probably do it by hand, but I do want to show you how to do it in a calculator. Okay. So these are dice rolls, and I need this for goodness of fit. I need to put it in a table. So I first have to name it something. I have no idea what I want to call it. Why am I rolling this dice? I don't know. So I'm just going to call it fair. F-A-I-R, observe. O-B-S, right? So my fair observations was, we don't know if it is fair or not, but my observations were 42, 55, 38, 57, 64, 44. Those are my observations, right? Then what would I expect? So if it were fair, F-A-I-R, I would expect it to be 50, 50, 50, 50, right? Because I did this 6 times in a row, right? So that's our data there. This is a goodness of fit. So I'm going to do menu, stats, stat test, goodness of fit. We called this fair obs for observations. This one I called fair expect. My degree of freedom, I have 6, so 6 minus 5, minus 1 is 5. Okay. So we get a chi-square value of 10. 10.28. I didn't do that on purpose. Sorry. A chi-square valued of, sorry, I'm trying to hold my phone and do this all at the same time. 10.28. A p-value of 0.06. Oh, darn it. Right? Degree of freedom of 5. And the comp list doesn't really matter, but if I zoom in, the number that was the most off was this one. this next to last one was the biggest contribution. But I didn't get 0.05, so I don't have to follow up. Now, if I would have gotten 0.04, then I would have followed up and I would have said, I got way more 5s than I expected. Does that make sense? I expected 50 and I got 64 of the 5. So what can I conclude? All right, because my p-value of 0.067 is greater than 0.05, we failed to reject the null. We do not have sufficient evidence to support H sub A. What is H sub A? To support that the distribution of the dice is not fair. I want to be able to say that the dice isn't fair, but apparently this is just a very low probability outcome. Nice work, guys. This was a chi-squared goodness of fit.